All right, you ready, Denny? Okay. All right. Class.
Yes.
Okay. All right. So continuity. Continuity has to do with, is the roller coaster going to go off track? Do I have holes? Is it continuous? Is there jumps? Is there slides? Is there, you don't want roller coasters to have jumps at all, right? You don't want a hole in your roller coaster. Continuity at a number. Definition of continuity at a number. C is defined. It is continuous. That is, C is that should be the domain of F. Okay, so now add a number. So this one right here is going to be continuous at C because Y of F. So when I plug in the function, this is also equal to right here. Now this one right here, you notice the limit works, but there is a solid dot right here. So the limit works, but it's not equal to the function at that point because this is equal to at a different point down here. This normally happens when you see like a piecewise type thing. This one right here, okay, the left and right side, so the limit goes there, limit goes there. They both, so limits are equal, so the limit does exist, but it's also possible to be undefined. That's the hole that we were talking about on our warm-up then that we just did. This one right here, this one's going to be a jump. Okay, so I have the limit from the left side goes here, limit from the right side goes here. They go to different, so the limits aren't equal, but the function itself is defined, but it is neither of the limits. So it's not going to be left or right. And then right here, when it's just the limit goes here, left side, limit goes here, right side, and then there is just a big hole. Nothing is equal to at that point. Determining whether a function is continuous at a number. Okay, determine if this is going to be continuous at a number. First thing we have to do is we have to look for holes or things that might give me discrepancies. Things that are going to give me an I, which is an imaginary number. So I get i's from the square root of a negative number, right? Okay, so that's going to be key. There is a domain restriction on those. This one right here does not have any domain restrictions. If I look right here, this is what type of shape? It is a parabola, yes. Thank you. All right, so it is a parabola. There is no discontinuities in this parabola. There is no places that I have to worry about where it cannot be equal to 0. So this one is going to be continuous at 1. This thing right here, I have a fraction. So in a fraction, right here, I'm going to plug in. And then, am I going to be able to plug in everything? Say no.
No.
No. Do you know why? Yes. Denominator equal to 0. So I got to worry about that. So there is places where this one would not work out. So I'll show you a couple ways of doing this. So I take the bottom, which is x squared minus 4. I set that equal to 0. I'm going to set the denominator equal to 0, and that's going to give me where my discontinuity is, where I'm going to not be able to do this, and where it's going to give me, in this case, probably holes. Yes, holes. Actually, not holes. These are asymptotes. Anyway, so I'm going to start by adding 4 to both sides. X squared is 4. X equals plus or minus the square root of 4. X equals plus or minus 2. Whenever I take the square root of something, I need to have a plus or minus there. So the plus or minus is going to be key. So that means that x would give me a 0 when I plug in a positive 2 or a negative 2. Those are my discontinuities. So in this case right here, x cannot equal plus or minus 2. So let's go back to the question. Is this continuous at 2? No, it is not continuous at 2. I made coffee if you need some. Okay. It's not continuous at 2. There is a discontinuity there. Determining whether a function is continuous at a number. Okay. Now, I have to take a look at a couple different things. But the first thing is inside a square root. So whatever is inside a square root, that has to be, whatever's inside there has to be greater than or equal to 0. If the number's inside, so right here, the numbers inside, if that's less than 0, those are negative numbers. Can I have negative numbers in a square root? No. Those are going to be imaginary. So I cannot use those. That would be another hole, another problem. Another thing, so my denominator cannot equal to 0. By looking at this right here, let's take a look at the top numbers first. The top numbers. Is there any way that my top numbers is going to give me less than 0? Is there any x value that I could plug in that's going to give me less than 0?
Less than 0.
Give me a number that might work.
0.
0? Let's see. So square root of 0 squared plus 2. What is that going to give me?
Oh, it's the plus 2 looking up there. Okay, I was going
Just the numerator. What's that going to give me?
to give me 2.
That's going to give me 2. Okay, that one did it. No problem there. So your whole goal is to find something that makes this fail. What if I throw in a negative number?
It would still be positive.
Why would it be positive?
Because it's squared.
Very good, because it's squared. So even if I throw negative numbers in there, it's still going to give me positive because when I square it, even the negative number becomes positive. So I don't have to worry about anything in the numerator here, right? Numerator is okay, so I don't have to worry about that having any problems with values that's going to be undefined. Now, the next one, let's look at the bottom. So x squared minus 4. You should automatically think that that one right there, I identify that as being what?
Perfect square.
Starts with a D.
Difference of a square.
Difference of squares. So on the bottom, I'm going to have x plus 2, x minus 2. And then my top will just stay the same right now. X squared plus 2. So let's take a look. And I know my denominator cannot equal 0, right?
No, okay.
So let's see. If I plug in negative 2, if I plug in negative 2 to this first one here, what do I get?
0.
I get 0, right? And then because this parentheses is being multiplied by the other one, anything times 0 is
0.
0. So this negative 2 would make this one here equal to 0. And this one right here, this 2, so 2 minus 2, would make the second one equal to 0. Right?
Yeah.
So this positive 2 will make this second one equal to 0. Even though if I plug it in, it would be 2 plus 2 is 4. And then 2 minus 2 is 0. And so, but anything times 0 is still 0. So that means it's 0 in the denominator, so it is not continuous. So those points are not continuous. You know, now those points are not continuous, but the next ones, what about 0? Can I plug in 0? Let's see. I didn't have any problem with it in the numerator. So let me see. Do the math right here. I'm going to get square root of 2 over. Is that a problem? It's a radical, but there's no negative in the radical. Is there 0 in the denominator? No. This is a real number, isn't it?
Oh, okay.
It is a real number, so therefore it is on my number line. It is continuous. So yes, it's ugly, but it's still going to work. So it is discontinuous at 2 and negative 2, but it is continuous at 0. This is what my graph looks like. So again, I have asymptotes right there. I have vertical asymptotes at 2 and negative 2. But this piece right here was continuous at 0. So that's looking at this using a graph. I could tell they're not continuous here. Now, determine whether a piecewise defined function is continuous. We have to see if it's continuous at 3. So that means that the left side, the right side, and the function all has to equal the same value. Left side, right side, and the function equals the same. Okay, so let's start with this middle just to see. So if x equals 3, my value is 9. Good. What if I plug in over here on the left-hand side? What if I plug in a positive 3? What's going to happen if I plug in positive 3?
Positive 3, it would just equal.
The top one.
Oh, the top one, it would equal 0.
On the denominator, right?
Yeah,
Denominator would equal 0, so I can't do that, right? Okay, so I know it can't equal 3, but I gotta see what this is going to be. So I know that by looking here, I got x squared minus 9. Is that going to give me a whole?
Yeah.
So x squared minus 9 is going to be x plus 3, x minus 3, over x minus 3. I can cancel out my x minus 3's, and I get x plus 3 and what was I trying to plug in there? Trying to plug in 3. So now can I plug in 3?
Yes.
Okay, so 3 plus 3 is 6. Okay, so far I already know it doesn't work. But let's continue. So what if I plug in the right-hand side? The bottom one's the right-hand side. So for x is greater than 3, that's going to give me where I have x squared, which is 3. 3 squared, right? 3 squared minus 3 is 6. So if you notice, there's not an equal sign on this one or this one. So what this is saying is my left side goes to 6. My right side goes to 6. But it's equal to, I get a solid dot right here at 9. So the limit is not equal to the function. So is this one continuous? No, it's not. Is there, if this is your roller coaster, would you want your roller coaster to have a hole right there?
Okay, so that's the whole one.
There is a hole right there. Okay, even though that there's a hole in the roller coaster. That's my analogy. Not like hole, this gives me a hole. This thing gives me a hole. Okay? This right here, in my analogy of a roller coaster, okay, being continuous, you want it nice and smooth, no holes, right?
Oh,
No
so
breaks, nothing.
a solid line. Solid
You want a solid line now for it to be continuous, but here it's not because at 6, I'm sorry, at wherever this is, at 3, you're gonna fall down somewhere.
Okay.
So this is not continuous. It is discontinuous. All right. Let's see. Definition: removable discontinuity. Let a function that is defined everywhere on an open interval containing c except at possibly c the number c is called a removable discontinuity. That's that hole that we're talking about by canceling them out. F, if the function is discontinuous at c, but the limit exists, the discontinuity is removed by defining or redefining the value of f at c. Okay? Left side and right side both go to the same point, but the function does not exist there. That's what that means. We just removed it by canceling out. Determine whether the floor function is continuous at 1. So let's bring up a floor function. So on your calculators, wait, it doesn't take too long. All right, you guys finding your calculators?
Yeah. Go ahead.
Okay. What the French toast? Be so mad if this thing doesn't work again. Get tired of this. Hmm?
How much is the printer?
Depends on what specialty you want.
Just print black and white.
Okay. All right. So, I'm talking you people through this on here, but now you are going to go to Scratchpad, go to your graph,
Okay.
go to your graph, and we're going to look for the floor function. No, it's not absolute value. And it is A, B, C, D, E. Come on now. You could the easiest way to do it is this is a floor function. What it means is that it is always going to round down to the lowest value until it gets to the next value. So what you can do is where it says f of x, type in the letters floor. Floor, open parentheses, put your x, close parentheses, and enter. Now, if you notice, this is not a regular absolute value bracket. There's a couple different that you can see. This, it actually has little L's. It goes on the bottom, right? So if that's a floor function, what do you think this one would look like? What do you think this one would be? Ceiling function.
Ceiling.
Yeah. So that would mean it would always round up to the next problem, to the next integer.
Like whole? Okay. No.
It's always going to round it up. But this one's a floor.
Okay.
All right, so now as you're looking at your graph, you can go menu,
Does it look like staircase?
hit menu. Yeah, looks like a staircase. Trace, trace graph, or graph trace. So my x values, as they keep increasing, the y value doesn't change, right? So if you're doing the trace, y value is not changing. But as you keep tracing it over, as soon as you get, wow, this is as soon as you get to 1, it automatically jumps up to the number 1. You can just type in number 1 if you want, or type in 2 and it'll jump to that location. And even if I go 2.99999, okay, it's still going to be there. So, is this one the roller coaster you want to be on?
No, absolutely not.
Is it continuous at 1? For it to be continuous at 1, my graph, the left side, okay, where this is 1, right? Okay, this one's going to go at 1. Yeah, I believe it's 1, isn't it?
1, yeah.
Okay, and the right side have to go to the same number. That's a number 1, not just a weird dot. So in this case right here, my left side goes to 0, my right side goes to 1. So is this one going to be continuous at 1? Say no. It's equal at 1. It's a solid dot at 1, but the left side and right side are not going to be the same place, right?
Yeah.
So I want that point to be continuous. So this one's a no. All right, I'm going to leave off here, and we're going to pick this up again on Monday. On Monday. So if you notice, as soon as I get to this next dot, it becomes solid over here. So we're going to continue right here. Monday, whatever slide this is, hold on to this one. And I want to give you time to start working on some of these problems. Make sure you like, share, and subscribe. Hit that notification button.